Previously on Witty Genius, Newton gave us gravity, 3 laws of motion, and the math that help humans reach the moon. Today, the tools behind the genius. The calculus he invented to make his physics work, the prism experiment that broke light into pieces, and a telescope he built in his bedroom that outperformed the professionals. Welcome back, Sir Isaac.
I trust this episode contains fewer falling objects.
Just light and math.
An improvement.
Your laws of motion are brilliant, but they have a problem.
Do enlighten me.
They describe a world that won't hold still. Rockets accelerate, planets curve, even your apple speeds up as it falls. So how did you calculate motion that changes every instant, using mathematics built for triangles and circles?
With great irritation at first. The geometry of Euclid was built for static forms, perfect shapes that do not shift. But falling bodies accelerate. Orbiting planets curve continuously. I required mathematics capable of measuring how quantities flow and change from one moment to the next.
So you invented new math?
I developed what I called fluxions, a method for calculating instantaneous rates of change.
We call it calculus now, one of 2 early versions that changed math forever. And it's the reason physics students both worship and resent you.
I accept full responsibility.
Explain fluxions, no equations, just the idea.
Consider the falling apple once more. Its height decreases continuously. Its speed increases continuously. At any given instant, what is its exact speed? How quickly is that speed changing? Traditional geometry could not answer this. It dealt in completed shapes, fixed distances. My method treated quantities as fluents, values that flow over time. The rate at which a fluent changes is its fluxion.
So, the thing changing is the fluent. How fast it's changing right now is the fluxion.
Precisely. With this, one may calculate acceleration, predict orbital paths, describe anything that changes smoothly.
And you can work backwards, right? If you know the speed at every moment, you can figure out the total distance traveled.
Indeed. Given the fluxion, one may reconstruct the fluent, as you might trace a journey from a record of speeds. It is remarkably useful for a piece of mathematics invented out of frustration.
Today, that math runs spacecraft trajectories, weather models, stock market algorithms, and the physics engines behind modern video games.
I remain uncertain whether I should apologize or accept praise.
While inventing calculus, you also locked yourself in a dark room with a piece of glass.
The plague years offered ample solitude.
Let's talk about your prism experiment. You didn't just make a rainbow, you proved something no one had realized.
The prevailing belief was that white light is pure, and prisms somehow create colour by corrupting it. I suspected otherwise. I darkened my chamber, allowed a narrow beam of sunlight through a shutter, and passed it through a triangular prism. The light stretched into a band of colours, red through violet.
Standard rainbow.
Not yet conclusive. So I isolated one coloured beam, say red, and passed it through a second prism. It did not split further. It merely bent. Then I recombined all the separated colours with another prism. The result, white light restored.
So, the prism wasn't adding color. It was sorting what was already there.
White light is composite. The prism separates its components because each colour bends by a slightly different amount.
And that discovery immediately caused a problem for every astronomer alive, because all their telescopes used lenses.
Precisely. The great refracting telescopes bent light through glass lenses, which, like prisms, bend different colours by different amounts. The result was chromatic aberration. Stars appeared surrounded by coloured halos. The larger the lens, the worse the distortion.
So, astronomers kept building bigger telescopes to see farther, and instead just got bigger rainbows.
An elegant summary of a deeply frustrating era.
Your solution was radical.
If lenses introduce colour distortion, abandon lenses. I designed a telescope using a curved mirror as the primary light-gathering element. Mirrors reflect all colours equally, no separation, no aberration.
Walk us through it.
Light enters an open tube and strikes a concave mirror at the base, which focuses it back upward. Before the light exits, a small flat mirror, angled at 45 degrees, diverts it sideways into an eyepiece where the observer looks.
So, light goes in, bounces off the big mirror, bounces off the small mirror, then into your eye.
Correct. The device was compact, roughly 6 inches long, yet rivaled the performance of refracting telescopes several feet in length.
And when you demonstrated it to the Royal Society,
They were impressed enough to elect me a fellow shortly thereafter. It revealed Jupiter's moons with clarity and avoided chromatic blur entirely.
a homemade bedroom telescope that embarrassed the professionals.
I would not phrase it so unkindly, but yes.
So, between 1665 and 1668, mostly alone during a plague, you developed the mathematics of change itself, showed that white light is composite, invented a new kind of telescope.
I simply pursued questions that refused to leave me alone.
Today, that calculus powers everything from rocket launches to AI neural networks. Your reflecting telescope design has been scaled up into the Hubble Space Telescope, the James Webb Space Telescope, giant mirrors in space staring at galaxies over 13 billion light-years away.
The instruments have grown vast, but the principle remains. Ask nature a clear question. Build the tool needed to hear the answer.
Not bad for someone working by candlelight in a locked room.
The room was quiet. The work was anything but. The universe rewards stubbornness.
On that, Sir Isaac, we agree. From a falling apple to galaxies 13 billion light-years away, all because one man refused to stop asking why. This is where we leave Sir Isaac Newton. Thank you for staying curious. Witty Genius continues, with new minds and new questions worth slowing down for.